Very good. So yeah, evening everyone, and again, thanks a lot for joining us. You know, it is module 3 now of Awakening, which is mass flow rate, as it says on the screen there. It's actually quite a lot more than just mass flow rate. This is, you know, talking about the principles of how we move energy around a house and a heating system, really. So to me, I think this is like the biggest unit that you can sit during the Heat Geek course, because in a way, and this was maybe the moment that it humbled me doing this course originally of, oh, actually I didn't know that, and I've been, you know, fixing and fitting boilers for whatever it was, 10 years at that point or something, and it was sort of a little bit humbling of like, why didn't I know this? So, you know, for people that are just starting to move into this space, I think learning this module, I think this is the bit where it's like, bang, you get it straight away. It's like, I need to dive deeper into, you know, the rest of the course, which I think it's nice where it sits in this course as well. You know, you done module 1, which is, you know, your what is energy, which is basically all your scientific principles and all that kind of stuff. Obviously then what we did last week was the heat loss calculations, which again, most important part of, you know, doing an actual design of, you know, like you can't do anything else after if you've not done that correctly. But then straight away, this is the bit now where it's like, okay, we know how much heat we're losing. How do we start putting this energy into the property? And it's this bit now, which is like, it's the light bulb moment for a lot of people, and it's the humbling moment for a lot of people as well. And I'll show you what I've done with this in terms of trying to like sort of push that message a little bit for people, especially if you're coming from the gas boiler industry, as quite a lot of people are doing, obviously. So yeah, as I say, thanks a lot for joining. It's nice to see there's some new names on here as well, and you know, hopefully, you know, you stick around and you continue coming to these. They are every week, and again, we do a different module every week, and you know, it keeps progressing. Hopefully, you know, we'll get onto the mastery ones as well after the Awakening, and people will stay with us, and then we can probably take you through the whole journey as well. And it'd be nice to, you know, see people finish. And again, I know there's people on the course, so likes of Stevie, who have, you know, already completed the course and, you know, even been verified and are now Heat Geek, verified Heat Geeks. And you know, it's nice that these people are still on here, because this is what we want to promote. We want to promote this peer-to-peer learning. So, you know, like the guys who are already putting messages on the Facebook groups and supporting others, like this is another way of doing it, where you're literally talking to people as well. And I love to see this, where people are still coming back and still being part of this, don't want to get cheesy, but part of this community really, and helping other people along, because again, that's what it's all about. So yeah, thanks a lot for joining. Again, a little introduction. I won't go too crazy on this. I did a full introduction last week about how Heat Geek sort of changed my career and all that kind of stuff, and you can see the recording on that last week. For the people that, you know, are new to this, I'm Lewis. I'm the training manager at Heat Geek. And again, I'd never like to start this off with, you know, it's talking about me, because in a way, like, I don't know if anyone else agrees with this, but as soon as someone says, you know, we'll start any conversation with, I have 30 years in the industry, like usually I'm not a fan of what comes after that, and you know, I just switch off. So it's definitely not going to be that. All I'm going to do is keep it brief. You know, as I started off as a gas engineer, so you know, the reason I'm saying that is because I'm thinking of quite a lot of people have been the same, and you know, how I transferred into, you know, low temperature to start off with, but then obviously into heat pumps. And I think this is a key message from this course, is it's not just centered around heat pumps. And I think this module sort of makes you think about that as well. And I think that's probably something that we're maybe doing wrong in the industry a little bit, is that we're trying to focus too much on heat pump installations in terms of the training. Like what we've actually got to do is focus on the low temperature side of the training, and then you can start relating it to your gas boiler installs. And then once you start putting it into practice, then that teaching just naturally takes you to the heat pump side of things. So again, a little introduction for myself there is that I was a gas engineer. I moved to Australia, fitted my first heat pump in 2018. It was crap. I know it was crap because I had no idea what I was doing. And to be fair, I didn't know what I was doing until I started doing the Heat Geek course. And I say it's that humbling moment then, like, even though I thought I was good, it's only when you actually see it on the screen and you're like, right, okay, I didn't know that, and I should have known that 10 years ago. Yeah, and then moved into teaching 2021. Again, I was also crap for maybe the first year, and I was teaching students, you know, and again, looking back, it's you know, it's quite humbling again, because you know, I thought I was amazing because I could teach someone how to wire an S-plan system without a sheet, and it's sort of like, you know, everyone's seen you as like a god for doing that, and then you look back at it, you go, I should have been telling them straight after I've taught them that they shouldn't be fitting S-plans anymore. They should be doing priority hot water. And then like, it's all these things that are like, it's these light bulb moments of like, oh, I thought I was great. I thought I was a god. And then suddenly you're like, oh yeah, I actually had no idea what I was doing. So yeah, and again, it all comes from this course. And as I'm saying, I hopefully like people can relate to where I'm coming from here, and the way I'm doing this training is because it's literally what happened to me. And this is why, I think this is so important. So again, not going too far on that. For the people that weren't here last week, slight recap, there's a video. I put the link on the Awakening course. So again, if you wanted to look over what we did, it was the heat loss module. I'll just pick 3 screenshots here of 3 of the key things, just in case you are interested in looking back at that if you wasn't here last week. So big thing was basically showcasing the apps that we use at Heat Geek. If you became a platform installer, if you wanted to learn about that, just drop us a message. I could talk you through it. So basically working under Heat Geek's umbrella, you get access to all the apps. Again, in terms of heat loss, saves you so much time, increases your accuracy, all that kind of stuff. But again, the key message behind this was, what's the theory behind the apps? And again, we talked about so many different things, and there was so much like great interaction between everyone as well. Of why we change air change rates and how we can get things more accurate and things like that. So again, introducing the apps, but also the theory behind them and how we actually use them day to day. That was a big key learning on that, if you wanted to check that out. Next bit was the importance of HTC, or basically how the heat loss changes. It's a heat loss of 7 kilowatts, but at what? It all depends on your outside temperature, inside temperature, all that kind of stuff. The importance of that is, obviously that's why we need weather compensation, because it's constantly changing. And then the final bit was, again, hopefully people took that in the right ways. Like, we've done all that learning, we've gone deep and everything, and the final slide was basically, you're probably wrong anyway. And again, it's a saying that I like to use a lot, because it's real life. You're probably not going to nail the heat loss calculation 100%. And that's why we don't advise people to set the curve at whatever you thought it was going to be based on that heat loss. Set it lower and keep going lower until you realize that you're not hitting that temperature anymore. And then suddenly, okay, that's heat loss now. That's where you. So again, I think that like this slide was just sort of trying to emphasize that of, do the calculations, use the apps, get as close as you can, but then in real life, let's start thinking about things as well. And again, that's what the whole course is about. Is it's not just the knowledge, it's how you actually apply this into the real world and talk to the customers and all this kind of stuff. So that was last week's recap. It goes obviously in a lot more depth on the recording if you're interested in that. Okay. Again, a little bit of an agenda. It's been on every week. Apologies for the people that have literally seen this probably 20 times now. It's not death by PowerPoint. The slides are just a guide for a conversation. Please get involved. As I say, don't leave any questions to the end as I'm talking. Press the hand button at the bottom. It'll tell me that you've got a question or you want to say something, like literally, even if it's just, I do it this way. Please do it. Please do it as I'm talking, just literally, I'll cut myself off because I'd rather you talk about it. And then final bit there is the aim to understand. It's not just to pass the test. I think we know in the industry that's the biggest thing that we need to tackle at the moment is everyone's just trying to get a qualification and get a certificate, which like literally mean nothing. And getting the Heat Geek qualification and the certificate, I think like that's what people should be aiming for in this industry personally. And I'm not just saying that because I work for them. But the aim of this is to understand that a piece of paper literally means nothing once you're in someone's house. So yeah, that's the aim of this whole thing. And then sort of moving on to what we're going to be doing today. I've heavily focused this towards gas boilers, and I've done this for a reason. And as I sort of alluded to at the start, is that I think the way that we're currently training people on heat pumps is wrong in a way. I think we're making too many assumptions that people already know low temperature, because why wouldn't they? If you're looking from the outside in going, well, we've been fitting condensing boilers, mandatory since 2005. Why don't we know low temperatures design principles? And I think coming from this background of myself saying, well, I didn't know how to do this. I think like we need to start promoting this more of, we actually need to learn how to design gas boiler systems to low temperature first. Because then once you start going into heat pumps, it's not a jump anymore. It's just like, well, I already do weather compensation. I already size my radiators based on a conversion factor for the lower temperatures. I already know how to pipe size. I don't use the rule of thumb of no one 3 rads off 15 mil. You learn these principles and you apply them on your gas boiler jobs day to day. So then when you go and fit a heat pump, you're not terrified for doing it wrong. You're just going to stick the heat pump outside rather than on the wall in the kitchen anymore. And like all the principles are still exactly the same. So in terms of when I do this kind of training, especially for this module, it's all based towards, as I say, I'm trying to humble people and like, oh yeah, you should have known this really, but no one ever taught you. And again, it's not your fault and it wasn't my fault. And again, it's probably the education system. It's probably the heating industry where no one really cared about teaching us about condensing appliances and low temperature systems when they should have. So yeah, that's how this is. So what I'm basically trying to say, I'm trying to teach you what your apprenticeship should have taught you in the 45 minutes we've got left. Because I know it's I'm coming from my own background. It's something that we need to pick up on really as an industry. So it's mass flow rate. This is the module. You need to know this triangle. So to pass this assessment or this module, and all the questions are sort of related to this, you need to have this etched in your mind or have it wrote down somewhere. Moving forward, get it etched in your mind. So we call it the magic triangle. It's actually the volumetric triangle once you start relating it to heating systems, but we call it mass flow rate triangle as well if you wanted to. If you've never seen these triangles before, the reason there's a picture of a hand on the side is literally you cover up the value that you're trying to work out. So if I was trying to work out what mass flow rate was, or what flow rate I need for a certain, whatever it is, pipe size or whatever, I would cover that up. And then I've got power over SHC times delta T. That's my calculation. So it'd be power divided by whatever the value in the bottom right-hand corner would be. If you are trying to work out what the power is, you cover that one up. And because mass flow rate and SHC times delta T are next to each other, you just multiply them two together and that'll tell you what your power. So again, same as most of the other triangles that you've probably seen in the industry. If you come from an electrical background, same as the Ohm's law triangle, all that kind of stuff, just cover up the one you're trying to work out. What I do in this module, I'll talk about each individual one. And that's why I sort of introduced this at the start of basically saying it's not just about mass flow rate, to be honest. Like a lot of these are probably, as important of understanding what these actually are and how they affect a system as mass flow rate, but we're calling it the mass flow rate triangle. So that's what we've got there. This is how we measure it. So you've got power at the top and we measure that in kilowatts. The bottom left, we've got kilograms per second, but if we're using water, we're actually going to use liters per second. So again, bottom left is going to be liters per second. And then on the bottom right, you've got your kilojoules per kilogram per Kelvin, which again is your specific heat capacity. And I will go into that more detail because it probably means nothing to anyone who, if they've never heard of this before or seen this before, multiplied by Kelvin. And Kelvin is just the scientific measurement for temperature, basically. And it's the same increments as degrees Celsius. So 1 Kelvin, moving up 1 Kelvin is the same as moving up 1 degree Celsius. Obviously, they're on different scales, and we won't go into that today. But again, it's quite straightforward. So again, if you see the K, it just means Kelvin. Just think of it in degrees Celsius in terms of this. Nice. So just to get into this before I actually break down the triangle in full. Sorry, someone just wants to join. So just referring to the components in the image below. So just them things you can see in that picture. Don't go crazy and start talking about other stuff in heating systems. How can understanding the magic triangle help you to design an efficient system? So you can refer to any of them components you can see on the screen. Anyone want to jump in and tell me why understanding that triangle helps you to design a system in terms of any of them parts on that picture there? Anyone want to jump in on that? What can it allow you to do? Alex, you got your hand up first, mate.
Can you find out obviously what flow rate you need to design it to by dividing the power by the specific heat capacity and then the delta T, so you can work out the flow rate, what's required?
Right, mate. Awesome, mate. Brilliant. So you can work out your flow rate. Brilliant. And then which of them components would affect your flow rate if you want to take that a little bit further?
The pump, circulating pump.
Nice, brilliant. Yeah, so your circulating pump. Yeah, so again, you can go into your control setting. You can say what your flow rate needs to be. Anything else that could affect that? Anyone else want to jump in? Any of them? What else could affect your flow rate on this?
Either of the other two can affect the flow rate. If you had more power or less power.
That's right. Brilliant, brilliant.
Maintain a set DT, it would change your flow rate obviously to suit.
Exactly. Nice, Stevie. Brilliant, mate. So again, yeah, they're all relative. So again, if you wanted to, well, Stevie, I'll ask you, if you wanted to double your delta T, what would happen to your flow rate?
So if you doubled your delta T,
yeah. So if I went from 10 to 20 delta T, what would my flow rate be doing?
You would half it.
Nice, mate. Brilliant. You'd half it. Yeah. So it's working slower because you're getting a wider delta T. Nice, Stevie. Cheers, mate. Awesome. So yeah. So again, flow rate vitally important for setting your pump speed, sizing your pump speed as well. Sizing your pump, sorry. But again, all these things can obviously interact with each other. Anything else we could use this triangle for in terms of, any of this kind of stuff? Like what else could we possibly size? What could we select based on this picture?
Pipe sizes.
Pipe size is nice, brilliant. So again, we need to know our mass flow rate so we can actually choose what pipe size we're going to use for this. And again, you can only find out your mass flow rate if you know how much power you're going to be sending down that pipe as well. So this is where, you know, the next couple of modules after this go into pipe sizing, because it's a nice, easy progression. And this is like your introduction. Once you know basically your power, you get your flow rate, and it's like, okay, what size pipe can I use? And again, you'll have a choice of pipe sizes. There'll be the optimum one, but you don't always have to use the optimum one, because you know, homes aren't always optimum when you walk in. You know, it might have to, you know, make a concession somewhere. But again, that like your pipe sizing comes into it. The size of your valves that you use and things as well, that all comes into it. You start going into pressure loss, which we'll get into as well. It's all relative to this. When you're balancing the system, again, you need to know your flow rates for that. How do you spread this heat out? How do we, you know, ensure that every radiator is getting the amount of heat that it actually needs, basically? So there's lots of things that, you know, this triangle, it's everything that you're doing with designing a system, basically. You know, after you've got that heat loss calculation, that's your power there just done, and then working out the rest of them, then like this is where this comes into play, and it is so important for an efficient heating system. So just on power, literally it's just this one slide on power, because you know it is what it is, and it's all relating to what we did last week, to be fair. Of, you know, you do your heat loss calculation. This is why you do a room by room heat loss calculation, so you can actually say, like, how much power do I need to send to that space? And, you know, just this example here where you've got the heat pump in the middle, you've got section A, which is your primary pipe work, and it branches off. So you've got section B there, and it's literally just feeding them 2 rads on the left-hand side. So again, you could do your calculations based on this. You could say, well, section A, how much power does that need? Well, it's the sum total of everything. You know, it's the 5 plus the 6 kilowatts. So section A needs 11 kilowatts. Okay, I'll put that into my calculation. What flow rate do I need there? Once you've got your flow rate there, you can start looking at all different stuff. You can start looking at what pipe size you need from that. What valves can you fit on that? And again, it's all relative. And we already know this kind of stuff, like on a higher level, because we're like, well, we know that the pipe work off the boiler or off the heat pump is bigger than what's going to a rad. But this is the science behind it, because the flow rate needs to be higher, because obviously it's carrying more energy. And this is where everything fits in together. It needs a higher flow rate because it's of the energy it's producing, or carrying, let's say. So again, why is the pipe work to a rad so small? Well, you know, if you take the far one on the right there, it's only feeding 0.5 kilowatts, so it can be small. Like you know, like we can work that out what it could actually be. And this is where once you see this on a screen, and it's like, I know it's so very basic, but it's like, oh yeah, actually them rules of thumb don't make any sense, do they? Because, you know, what's this rule of thumb of no more than 3 rads or 15 mil? It's like, yeah, but what was the kilowatt you're sending down? You could have been sending 0.1 kilowatt down to each rad, like, why, you know, or you could be sending, you know, 3 kilowatts down to each rad. So this is where you start to question rules of thumb of like, why has someone told me this in the past? Because this doesn't make sense in the real world, like in terms of physics. And, you know, you can look at this and you can learn so much from. This is what we're doing, basically. We're just moving power where it needs to go. Specific heat capacitor, again, if you're brand new to this, you may not have heard this in the past. So basically, top and bottom of it is how much energy is required to raise the temperature of a certain substance by 1 degree. Okay, so again, that's based on basically 1 kilogram. It says there, so it's kilojoules per kilogram per Kelvin. All it's basically saying is how much energy do you need to raise that by 1 degree Celsius or 1 Kelvin. Key thing you want to remember is the one on the screen there. Water, we use 4.2 kilojoules. It's actually 4.186 off the top of my head, but 4.2 fits nicely into our calculations. And for once, Heat Geek go into 1 decimal point, which is really nice for us, because again, it helps with this triangle as we move forward. So 4.2 kilojoules is the number you want to remember for water. Again, if you were to add salt to your water, or let's say you was making pasta and you were boiling your water on your hob, if you put salt into that water, does anyone know what happens? Does the water boil quicker or slower? Any ideas? No, it actually boils quicker if you put salt water rather than normal water. And if you're actually doing that, all you're doing is basically you're reducing the specific heat capacitor. Okay, because if you think about it, if you reduce the specific heat capacitor, it means it doesn't need as much energy to basically raise its temperature by 1 degree. So it would actually get to that 100 degrees where it starts to boil. I know it boils before that, but you know, it gets to 100 degrees quicker. So again, if you add salt to it, you're affecting its specific heat capacity. That's why it boils quicker. Terrible example because no one had any idea what I was talking about. Nice. Some more examples of common heating things, substances, materials and stuff that we use, just to give you a rough idea about where we're going with this. You don't have to remember these, it's just to sort of give you an overview of what we're talking about. Water is 4.2. Water is amazing. I've called it there the king of energy storage, because it's such a high capacitor, heat capacitor, that you can put so much energy into it that you can then use that energy. Okay, so all we're doing with this is basically we're just transferring energy from one place to another. Because water can store so much energy, it's amazing for heating our home, because then we can start sending that around the house. If you had something that was a really low specific heat capacitor, again, it wouldn't be great for transferring energy, because you can't get that amount of energy into it without obviously having issues there. So water 4.2. The next one down, again, vital if you've never been told this, or if you've been on one of these 3-day courses where they like to talk about glycol quite a lot. If you do a 25% glycol to water mixture, it actually reduces your specific heat capacity to 3.7, which basically means, when we do the maths, and I've shown you an example in a minute, is you actually need higher flow rates to transfer that glycol around the system, which again puts more strain on your components, it uses more energy, all this kind of stuff. So glycol, that's just one reason glycol shouldn't be used in a heating system, but there's many other reasons as well. So again, Heat Geek's advice is don't use glycol on your systems. It's not great. Viscosity is higher, it's bright pink. If it leaks on your cream carpet, you got issues. Like, there's so many disadvantages, but the one that we're talking about here is it's heat capacity basically. And again, I'll show you the sums as to why that is. Then you've got some common, materials that we use there. Copper. Like, why do we use copper? Well, it says on the notes there, it heats up and cools down quickly because it's got such a low heat capacity. So it's great for transferring energy, because it's going to heat up and it's going to send it across really quickly without having to wait for it to heat up. You've got your steel and your aluminium there. And again, aluminium is a higher heat capacity than steel. So it can actually, store more heat than steel per kilogram. It's also more efficient at conducting heat as well. So if you're interested in that kind of stuff, again, there's some examples there of why we use certain materials. Again, I won't dwell on that because I know it's quite boring. Getting back into the maths and understanding this, and again, for the questions that are in this module, if you are in this module or you're going to come up to this module, this is what you want to be looking at. You want to start doing some examples, because again, every single question is based around this triangle basically. So we've got water on the left and we've got glycol on the right. Okay, we got to the system. Let's say we need 10 kilowatts in this example. So both systems still need 10 kilowatts. We're trying to calculate the mass flow rate for these. So what flow rate we require in the system. So if we just look at water first, we've put our 10 kilowatts in. We already know that. We're going to be designing a heat pump system, and I'm going to get into delta T's and stuff as we move forward. But we've got a specific heat capacity. I've already told you that specific capacity of water is 4.2. You need to remember that one off the top of your head. So it's 4.2. You multiply that by your delta T. Now, this all depends on what appliance you're installing. And again, I'll go into the different appliances and what their delta T's will as we move forward. But for a delta T a delta T on a heat pump will be between 5 and 7. We're going to say 5 for this. So 5 degrees delta T. So my calculation, bottom right-hand corner, is 4.2 multiplied by 5, and that gives me 21. And again, in the real world, when you're designing a system, all you need to start remembering from now on, if you're designing a system for a heat pump, is the number 21. Because once you've got that, then if you're filling your system with water, and please do, it's always going to be 4.2 times 5 when you're designing the perfect system. So if you just remember the number 21, all you've got to do then is how much power am I sending down there? It's 2 kilowatts. Okay, 2 kilowatts divided by 21. I'm sending 4 kilowatts down there. Okay, 4 kilowatts divided by 21. Once you get that, it's not a rule of thumb. It's just a quick calculation of something you've already worked out. Again, some systems you might need to go a little bit of a wider delta T, depending on whatever you're facing, which is fine as well, as long as it's an actual calculation and you're not just doing it for the sake of it. But again, you want to be designing at 5 degrees ideally. So again, we've got 21 there. So again, I think we know this, but the calculation will be 10 divided by 21, and that would give us our flow rate there. Glycol, exactly the same. The only thing we've changed is the 3.7. So instead of 4.2 heat capacitor, it's actually a lower heat capacitor, so it can't carry as much energy. So it's now 3.7. Once you put these two into a calculation, I thought they both appear there. So once you put these both into a calculation, it tells you that you need 0.48 liters per second for your water. And you need 0.54 if you're using glycol. So again, you need a higher flow rate to still maintain that same power output, basically, if you're using glycol. So again, this is when the science and the physics and stuff come in. It's very straightforward, though. It's literally put it into a triangle. It's all there for you right in front of your face. But again, it's one of the disadvantages of using glycol, and it's there on paper. If you were just to do the same flow rate and you didn't do this calculation, you thought, oh, it's just, divide by 21, but you actually pour glycol in, you're actually going to be reducing the amount of power that you can output from that system. So again, you're going to have issues with that as well. So just an introduction to the triangles. They all work exactly the same. Hopefully that makes sense for people. Okay, this is where we start getting into it now and start basically assessing what we should have been taught when we did our apprenticeships. If your apprenticeship was like mine, when the condensing boilers were already out, I was like, why have I never been told this in my life? I was told this, but we just forgot it. But what is the target delta T for a condensing boiler? Anyone know that? Anyone want to jump in with that? So what's the target delta T for a condensing boiler? And that's between flow and return at the appliance. So someone say something then, sorry, I didn't catch that. Stephen?
20.
20? Nice, mate. Brilliant. So for a condensing boiler, for a modern condensing boiler, you want a delta T, or a difference in temperature, of 20 degrees. And again, if you wasn't on last week, that triangle is delta and T is of temperature, so it's difference in temperature. So at the appliance, if you put your temperature clamps on the flow and the return, you ideally want a difference temperature of 20 degrees. Anyone know why? Why do you want such a wide delta T on a condensing boiler?
Promote condensing.
Promote condensing. Nice, mate. Nice. Do you want to expand on that a little bit more? Why does having a wide delta T promote condensing?
Well, if you've got a 70-degree flow where delta T 20, your return would be 50, and I think it's under 54 degrees is the dew point. So as long as you're under that 54, you should, and obviously the lower you do get, the more condensation you're going to get. So if you're running at, say, 55 flow and a 35 return, you're going to even get increased condensing again.
Awesome, mate. Spot on again, mate. Love it. Brilliant. So yeah, so as Stevie said there, exactly right. And I'm glad he was, and I'm glad one of us is right, because we're both for the same number here. That dew point is 54 degrees. And again, like, this should have been number one thing you learn as an apprentice, if you've done your apprenticeship in the last 30 years, let's say, which I think most people probably have. Like, this is what we should have been taught of. Get that return temperature down as low as possible for your condensing boilers. Once you do that, your efficiency shoots up. So this table here is taken from my first book, found on Amazon, if anyone wants to look at that. The return temperature is on the bottom, and you've got boiler efficiency up the side there. So again, as you're basically moving down, your return temperature is getting lower and lower, your efficiency is shooting up. And again, as Stevie said there, like, if you set your flow temperature at 70, like, please don't, but if you set your flow temperature at 70 and you had a delta T of 20, so your return was at 50, you're actually below that dew point, you're actually in condensing mode. And if you follow it across there, like, it's quite interesting to see that it's not even 90%, it's only like 88 or less than that, 87%. So, but again, if you were to set your flow temperature at, let's say, 40 and you're at a delta T of 20, if you look at where 20 is, suddenly now you're at like nearly 96%. It does make a difference, and it's quite interesting to actually see this. And I think if we go out to boilers and we're like, everyone's looking at boilers saying, oh, it's old technology and stuff. And like, yeah, it is old technology compared to a heat pump, but most of these boilers aren't even condensing anyway. Like, they're not even doing what they're meant to do. Alex, do you want to raise in something there, mate?
Yeah, is there like what's the lowest flow you could go with a boiler then? Because obviously you don't want to go too low, I'm guessing, because then you'll have more condensation. Yeah, am I correct in thinking that? Or can you go as low as you can?
You can go as low as your boiler will take you. There is a
Brilliant.
slide on this, and I like that you've asked that, because once you get into this, you suddenly become like a snob with boilers, because like, you suddenly like, oh, that boiler's a lot better than that boiler because it can do this. But yeah, the lower you can go, the better. Stevie, do you want to jump in there, mate?
Yeah, obviously you've got to pay attention to your radiator sizes as well, though, because the lower your mean water temperature, then you're going to end up with massive radiators like it.
Exactly. Great point, mate. Great point. And again, once we get into the radiator one, this all comes into play as well. But yeah, Steve is completely right there. If you're setting your flow temperature really low, let's say you're setting it to 30 and your delta T of 20 and your return was at 10, that's great, really efficient, but you probably can't get into your house because it's just full of radiators. And it's like these kind of things where there probably is a limit. Well, there is a limit in most properties, but yeah, there's a lot to think about. But yeah, good question. And again, like, I think, like, you know, that the key point from this is we need to start getting these flow temperatures down on our heating systems, no matter what the heating appliance is. Every modern heating appliance needs to have a lower flow temperature. If it has a lower flow temperature, it has a lower return temperature, it's more efficient. And once you start putting these practices in on your gas boilers, suddenly you start looking at gas boilers going, I'm limited here. And if you look at this, you know, you can't have a 100% efficient gas boiler unless you were trying to kill someone. You know, like you're going to lose heat out of that flue. It will never be 100% unless you turned it around and stuck it in someone's kitchen. And then obviously, you know, you'd probably get sent down for that. You know, well done, you got a 100% efficient heating system, but, you know, so again, you're limited with gas boilers. And it's something that I sort of want to start promoting, because once you start getting into this and you start designing gas boiler systems like really well, you naturally gravitate towards heat pumps, because it just becomes more interesting, because you've got so much more power in your hands of like, well, actually I can increase this by 100% or 150% or 200% if I properly dive in on the design on this. And I think this is like the sort of message I'm trying to promote here is, like, let's start looking at it with gas boilers first. And once we start getting gas boilers right, you'll naturally just move into heat pumps, because it's the natural progression. It was a natural progression for me, because it becomes more interesting because you're limited there. And, you know, like, without going too far on this, like you could spend $2,000, let's say, repiping the full system in this scenario and replacing every radiator to get your flow temperature down by 10 or 20 degrees. And then you look at this table and you go, oh, great, I've spent $2,000 and I've raised the efficiency by 5%. And it's like, oh, yeah, what does that equate to in money that they're spending every month? And it's like, well, nothing. Like, what was the point? If you did that with a heat pump, like, suddenly it shot up, and then all this just sort of, yeah, it just becomes, yeah, a little bit more interesting anyway. So brilliant. And as Stevie mentioned before, you know, you are increasing the condensing side of this as well. So that has benefits for the heat exchanger. It cleans the heat exchanger itself. You know, gas boiler's probably going to last a little bit longer as well. Well, it will last longer if it's in condensing mode for longer. Sorry for the terrible images there, but, you know, this is the only one I could have to hand. But so what we've got there is, you know, you got your cylindrical heat exchanger there. You've got your return temperature coming on your right. It's coming in at 45 degrees in this case. Again, it's at condensing mode. So what's going to happen there, as you can see, is as the flue gases are coming out through the heat exchanger, it's just going to condense onto that pipework. Because if you think about what condensation is, it's when the humid air comes into contact with a cooler surface, and that's all it basically is talking about. You know, breathing your hot breath onto a cold window, you get condensation. And that's all this is. And this is why we need a lower return temperature. And I sort of want to emphasize this point. It's not just this is because how it is. Understand why. And once you understand why, you'll remember it. So again, if you're sending a hot gas at a hot pipe, it's probably not going to condense because it's already hot. If you send a hot gas at a cold pipe, it's probably going to condense. And again, this whole principles that you've learned in school and you've learned throughout this course of like something hot will always move to something cooler, it applies here as well. You know, your flue gases, as they're rising up about to go out the flue, they're cooling down constantly. If they're hotter than the pipework that they're about to hit in the heat exchanger, they're not going to transfer their heat into that water. They're going to go straight out your flue, and then, you know, it's going to be sending all that heat out into your garden and eating up your garden, which nobody wants. You want as much of that energy that you've just paid money to set on fire to basically be transferred into that water that's in your heat exchanger. So if you look at that image there, like that middle ring of the heat exchanger is getting heated up directly by the flames, basically. And again, like really simplifying it here, but as it gets further out and further out, that outer ring is actually getting heated up by the flue gases. If that outer ring, the return temperature comes in at 60 degrees, them flue gases that are already near that temperature are going to look at it and go, I'm not going to transfer my energy, I'm going to go to outside. So this is like the science behind it. And it's very simple. It's just like literally something hotter is moving to something cooler. Get them temperatures down as low as possible. And then on the right there, we've got an image of a boiler. I won't say what boiler it is because I'm going to call them out in a minute. But like you can see there, like where it says boiler output, what I've circled. In non-condensing mode, the boiler output on this, an example, is 24.2 kilowatts. If it's actually in condensing mode, so you've dropped your mean water temperature, so your average water temperature inside by 30 degrees, so it's now at 40 degrees, you're actually getting like an extra 1.4 kilowatts out of this boiler, which is crazy. You've actually, imagine like trying to explain this to an apprentice or a customer, someone who's not been told this before, of like, you know, if you actually turn your temperature of your flow temperature down, you get more kilowatts for free. And it's like, that doesn't make any logical sense. But when you start thinking about what's happening with them flue gases there, them flue gases that in the, you know, in the 70-degree mean water temperature about to go outside, suddenly they're getting transferred into your heating system. You're getting an extra kilowatt or an extra kilowatt and a half out of this system. And again, it like this isn't a typo. And if you look at any modern gas boiler, their output tables, they're all exactly the same because they're all should be in condensing mode. As I say, once you get into the real world, you realize quite a lot of them aren't. I think they did a study and it's like 80%, or like the average efficiency of a modern gas boiler is like 80%. Like it's mad, like even though it was sold at an efficiency of 92 or 94 or whatever it says on the box. So that's that. And then again, this is where I said you start becoming a snob with your models, and you start looking at things a little bit different, and you'll get like this with heat pumps as well once you get into that. So the model on the left is a Wiesmann, and again, if you compare this of like basically how low can they actually get is my next point of, and it sort of comes into what Alex mentioned as well. How low can it modulate down to? Because again, we want these boilers to stay on for as long as possible. Same as the heat pump. If it's turning on and off all the time, you know, it's not going to last as long. And obviously, you get more issues when your heat pumps are cycling as well, in terms of the efficiency. But you know, if this Wiesmann here, like, let's take the you got 19 kilowatts to start off with, then you got 26. If you look at 26 kilowatts, it can actually modulate down all the way down to 2.6 before it turns off. If you look at the boiler on the right, a 24 kilowatt can modulate down to, where are we? Boiler minimum input is like 4.9. So again, the one on the right can only modulate down to 4.9 before it has to turn off. The one on the left can modulate all the way down to 2.6. You start comparing stuff and you actually get interested in your job again once you start learning about this, because it's like, it's not boring anymore. It's not just going out and pumping up vessels and changing Schrader valves and stuff. It's actually, how can I improve this system? How can I talk to a customer and get them interested in their own heating system? And you become a lot more interested in your job once you start learning about this kind of stuff, I think. So what was the target DT for a non-condensing boiler? Anyone have any idea what that used to be? Stevie?
11.
11? Nice, mate. Oh, yeah, nice. Nice. Okay, so we're either at 10 or 11. For the sake of this, I'll probably start talking about it as 10 because it makes my maths a little bit easier and it relates to something else, but it was 11, mate, spot on. So yeah, so we used to design non-condensing boilers to basically a delta T of 11. And the reason for that is because we didn't want to promote condensing, because we wanted to keep them flue gases, basically stopping them from condensing. We wanted them to go out that flue. So, you know, you go to these old balanced flues with a big square flue, it's like terminal. If you touch that, it's going to take skin off your hand because it's red hot. We're trying to get them as hot as possible. And the reason for that is because if it started to condense inside the boiler, all them cast iron heat exchangers, they're just going to corrode and not going to last for the 70 years or whatever these last for. So again, we want to stop condensing in them boilers. But I think like what I'm sort of getting at here, and the reason I wanted to put this in, is that message got lost when we moved to condensing boilers, and then we still just design as if we were designing non-condensing boilers because we were taught by somebody who had been taught that way, and we never got dragged back in for extra training or, you know, yeah. So again, I'll get off my box because I sound like I'm, you know, standing up doing town crier stuff here about this, but. So the next bit is lasting effect, and it's like, why are we still doing these things that we were taught when, you know, non-condensing boilers were the way of the world? So if you look at your radiators now, so your radiator outputs, again, a lot of them have got apps now that you can use where you can adjust this. But, you know, if you were just to buy a catalog, it would say Delta T50. And again, when we get into the radiator module, this will become apparent as well. But it's all based off that old non-condensing model of a 75-degree flow temperature, as it says there. You got a 65-degree return temperature. So your average or your mean water temperature in that scenario is going to be 70 degrees. You then got a 20-degree air temperature. So what they're saying is basically the difference between the average temperature of the radiator and the air temperature is 50 degrees or 50 Kelvin. So what they say is like my output of my radiator of this 600 by 600 is, let's say, I don't know, 1 kilowatt at Delta T50, and they give you them measurements. But again, if you're designing a modern system, you're not going to be using this, and that's why we have to do conversion factors, because it's no longer giving out 1 kilowatt if you've got your flow temperature to 40 degrees or whatever you're doing. So again, we're still stuck in the dark ages even now with this kind of stuff, because the radiator catalogs are still, the output is still based on Delta T50. It's still the lasting effect of what we had been doing. The next lasting effect is this, like on-off stats. Again, like the amount of people that still install on-off stats, and maybe without even realizing, like, it's called smart, and it's definitely not. Like, it's just the one on the right. I'm allowed to say, like, the Hive is, it's just a fancier version of the one on the left. It still does that. Okay, get to a target, turn off. Get to a target, turn off. It's a lasting effect of the non-condensing appliances where we had to do that. We had to send so much heat into that appliance because it couldn't modulate down. It would just keep going and turn off and keep going and turn off. So again, another lasting effect. This is me basically saying that I got it wrong. So this is in my mum's property when I fitted the boiler there, like maybe coming up to 10 years ago now. I didn't understand any of this. I still fitted it as if it was a non-condensing appliance. Like, I'd never been taught any different. I measured the delta T across there. As you can see, it's like 13 degrees delta T. If that was wider, it'd be more efficient. And again, it's just because I had no idea what I was doing. I just did what I was told. And again, it's like, it's only now after doing the Heat Geek courses and the Kimbo course and all these good courses, it's like, okay, yeah, I had no idea what I was doing. So another lasting effect. Final lasting effect is the S-plan systems and the Y-plan systems that we install. And again, like, you would not have to go into the crazy details on this, but if you look at the zone valves in the top right-hand corner, them orange wires are basically the switch live. They're the ones that tell the boiler and the pump to come on. And you can see they're actually joined together. So the boiler and the pump have no idea what the demand is. They're just like, oh, I've just got voltage, I should work. And obviously that has a massive effect on efficiency, because, well, what temperature do you want to run at? Are you heating hot water? Are you heating your radiator circuit? Like, what are you actually heating? Like, an S-plan has no idea about that, but yet we're still promoting S-plan, we're still installing S-plans, and colleges are still being assessed. Like, your final assessment is install an S-plan plus. Like, it's like the pinnacle of your career, and it's like, oh, what are we doing here? Like, this is not right. And again, it's just a lasting effect of what we've been doing with non-condensing boilers. We sort of need to move forward with this industry and just say, like, that's wrong. Like, priority hot water is the way to go. Again, I'm probably rabbiting on a little bit too much, so I'll try and give this along. Again, I'll use my mum's property as an example. So when that's literally, she did have that pot of Kingfisher in the corner when I took that out and put the combi in. And again, it was like 10 years ago. But the floor area of when the house was built, the floor area still is 86 meters squared for this. Just a mid-terrace, basically. The heat loss when it was built was probably around 8 kilowatts, and that's a rough example based on, it would have had single glazed windows, wouldn't have had cavity wall insulation, all this kind of stuff that's been improved over time, and loft insulation and stuff. So it probably had around 8 kilowatts heat loss. Over time, we've actually improved the insulation of our properties, obviously, because time's moved on. So again, now it's got double glazed windows, now it's got loft insulation, all this kind of stuff has basically brought that heat loss down. It's now around 3.5 kilowatts. So again, it's had a massive drop in basically heat loss. And there's just that table that we showed last week on the heat loss, the rough overview basically to calculate that. And again, what I'm trying to emphasize here is when I did this, when I installed the new boiler, which is a condensing boiler, like, did I change any of the rads? Well, like, no. Did I change any of the pipe work? Like, no. Like, what did I do? Like, did I even do a heat loss calculation? And I'll be honest, I didn't do a heat loss calculation. I ran the tap and seen how good the flow rate was, and then fitted a 28 kilowatt combi. Like I didn't do any of this kind of stuff that I should have done. And again, it's sort of emphasizing that point of we've been doing it wrong because we didn't know, because we weren't taught, and it's not our fault, and it's not anyone's fault really. It's people that should have been teaching us how to do this kind of stuff right. So the lasting effect is basically my mum's combi. That's why it's got quite it's got 13 degree delta T. It's because all the pipe work was sized for that boiler, that non-condensing boiler. All the rads were sized for that non-condensing boiler when it was massive heat loss. And then why is that an advantage, do you think? Why do you think the fact that I didn't do any of this stuff I should have done because I didn't know is now an advantage to me moving forward, do you reckon? Or for the industry moving forward? Why being so poor at this is actually helping us now? Stephen?
Because everything's probably already oversized. The time you take your deductions for your insulation and everything for upgrading. Everything would be more typically suited for a sort of heat pump.
100%, mate. 100%. Brilliant. So these older houses, as he says there, like you know, they're mostly oversized. The rads are oversized. The pipework's oversized for a condensing boiler. Like, but for a heat pump, that's great for us. Like, the fact that we were so bad at doing this, and I was so bad at doing this, means that when I fit a heat pump, it's nice and easy for me. Like, the rads are already huge. Like, I just, you know, didn't touch them. They were already sized for when the heat loss was massive. I didn't go out and start changing pipework and stuff when they changed from single glaze to double glaze. So, you know, it's already oversized. And again, like for heat pumps, it's actually a really good thing on older houses, which is weird to think about, that the older houses actually need less work than a newer build property, which, you know, has probably not rads that are sized properly. That's why they're like little postage stamp things that you know look awful. But, you know, like it's a bit of a weird thing to think about, that by not doing it right, we've actually helped ourselves transition to heat pumps moving forward. So again, yeah. So that's why we're talking about this now. So with the heat pump, the delta T for that, the target delta T for that, I'll just move it on a little bit. It's between 5 and 7. We're going to say 5 degrees for this. And again, as we emphasized before, it's a good thing for us because we can probably get that in most properties. You just got to be a bit smart where you actually connect your pipework in. So, you know, when you're doing your primary pipework, if you go into the center of that property and you can split that load across, you can probably keep most of that pipework. Obviously do the calculations, which will teach you, but, you know, because it's so oversized, it's actually probably okay for this higher flow rate. Because it was basically based on the non-condensing models. For the heat pump, again, this is why you want to keep a narrow delta T. The one on the left is basically, I'm also emphasizing the flow temperatures here as well. Again, we won't go into how the heat pump works and stuff. You probably learned that in Enlightenment. But basically, that one on the left there, you've got a low flow temperature, which also means that you've got a low return temperature. So that difference in temperature isn't very high. So when that water comes in, it doesn't need to be raised up by a crazy amount. That has a massive benefit on the main part of this whole system, which is the compressor. That's the only bit that is going to cost the customer money. The more energy that uses, obviously, the less efficient it's going to be. So again, if you have a wide delta T, let's say you've completely ignored everything we said and you design your system at delta T20 because you've got mixed up, suddenly when that return temperature comes in, you want to raise it by 20 degrees, that compressor's looking at that going, okay, I've got to do a bit of work here. It uses so much electricity to get that temperature up. And again, it's all related to the pressures, as you can see there. So in this scenario, you're raising from 3 bar to 10 bar, but basically all that means is that that compressor is not having to work as hard. The one on the right there, where you've set your flow temperature up to 55, that compressor now is having to work so hard to get that 3 bar, this is just an example, that 3 bar up to 19 bar there, that so much more pressure there being worked on this. And again, it's just an example of not just flow temperatures, but of keeping that delta T narrow, keep it running for as long as possible, and also try and keep that narrow so it's not having to work as hard to basically get that temperature up there. And that's why it's so important. So 5 degrees on a heat pump. And again, as I say, in most older properties where it's not had a lot of work done, it's probably already there. So, you know, there's not a lot of work to do, but always do the calculations on this. Just a little example as I like to use with people as well, just to emphasize this point. If you are designing a condensing boiler system, again, there's maybe arguments to not design to 20 degree delta T anymore. If you know, think they might move into a heat pump in future, you might sort of want to have that in the back of your mind as well. But let's say you were going in and you were just going to design it all to 20 degree delta T. You set a 45 degree flow temperature, you set your return temperature to 25, so obviously there's your 20 degrees. Your mean water temperature, so your average temperature of your radiators in that case, would be 35 degrees, so obviously it's just in the middle there, so that's a condensing boiler. And the funny thing is like if you then change to a heat pump, your mean water temperature is actually, you know, higher. It's 42.5 because your delta T is narrower. So again, if people miss that, your mean water temperature before was 35 degrees. Change to a heat pump, you've actually got a mean water temperature of 42.5 degrees. Again, that might save you so many radiator changes if you think about that. Or it's the argument of, or heat pumps don't, you know, heat your house or whatever, or your radiators aren't as hot to touch. It's actually, well, if you bother about how hot it is to touch, like it's actually hotter to touch if you know you have a heat pump. And again, you shouldn't really be emphasizing that anyway, because that's not important at all. But you know, it's little bits of knowledge that, you know, it's just getting lost in the industry for some reason. So just to sort of round this off and get back to the triangle and all that stuff I talked about there, it is important not just to pass the test. Like you will pass the test if you took all that in, because there's so many little nuggets and stuff there that are questions in this test. But the main thing there is the understanding and maybe that stepping back of like, okay, I didn't know that. I didn't know that we should have been doing that. And then it sort of, it makes you want to get interested, I think, in my opinion. So, but getting back more to, how we use this triangle. So what flow rate is required? This is a question, and it's relating to something that was in the test as well. What flow rate required is required in litres per minute if we have a 30 kilowatt heat source and wish to heat the water from 10 degrees to 45 degrees and round it to the nearest number. So anyone want to jump in with what calculation we're actually going to do here? Alex? You're on mute, sorry, mate.
Oh, sorry, it would be power divided by specific heat capacity times delta T, yeah? So would it be 30 divided by 4.2 times 35?
Yes, it would be. It would be
0.2.
Yes, nice, brilliant. Yeah, I think it is. Yeah, awesome, mate. Nice and quick. I like it. Awesome, brilliant. So yeah, so what you've done there is again, you knew your 4.2 for water. Again, vitally important to remember that one. So it's 4.2. Your rising temperature is 35 degrees in this example, because again, we're raising the water from 10 to 45. So our difference in temperature now is 35 degrees. So that bottom corner then becomes 147. That's 4.2 times 35 equals 147. Then once that number's in your bottom right-hand corner, it's as simple as 30 kilowatts over 147 gives you 0.2 liters per second. When you're doing the assessments, just be cautious of what the question is actually asking you. It's asking you for the number in liters per minute. So don't leave it as liters per second. So change to liters per minute times by 6 there, nice and straightforward. So again, we've got 0.2 liters per second. You're going to convert that to liters per minute. That gives us 12 liters per minute. So then I put all them numbers into there, and we just need a flow rate of 12 liters per minute in this scenario to raise the water from 10 to 45 with a 30 kilowatt heat source. Anyone have any idea, like once you look at them numbers, where have you seen this relationship before where it's 12 liters per minute, you're raising water by 35 degrees and you've roughly got around a 30 kilowatt heat source? What is that explaining? Has anyone ever come across that in the real world? Stevie?
That's a similar example for like a combi boiler.
Nice.
For your 10 degrees water coming in, 5-degree rise.
Brilliant, mate. Brilliant. It is. So yeah, so if you've ever, looked at a combi boiler and seen like what rise can you get from that incoming water with this size heat source, like they'll usually say you need your water at 12 liters per minute to get this rise. And when you look at that, it's like it's just a saying that you just know from being in the industry of like, oh, okay, 35-degree rise, 12 liters a minute, you probably need around the 28 or 32 kilowatt boiler. When you look at this is the actual science and the maths and stuff behind it. It's like, oh, that's why it's not just a rule of thumb anymore. It's actually science, and it makes sense. So you can use this relationship. We'll use it loads moving forward to do pipe sizing and things like that. But you can use this relationship in so many different parts of the industry that because it's just fact, it's just science, and again, you can't argue with it really. So yeah, that's just a nice little thing to think about. But the main thing is how you actually work this out. Obviously. So yeah, that's quite heat exchanger. So yeah, any questions on anything we've talked about there? Oh, brilliant. And again, I'm just conscious that I've talked a lot. So if there's anything you want to ask that you don't want to say in front of the group or anything like that, just drop me a message. You probably all got my email now. You can put it into support@heatgeek.com as well, and again, it'll get picked up. Facebook support groups, again, are all vitally important for this kind of stuff. Again, the next course support is on Tuesday. That's going to be pipe sizing. So it starts off with velocity pipe sizing, then it moves on to the resistance side of things as well, so the pressure drop side of things. Put them two together, that's how you know how to pipe size in future. Main thing there is we're trying to work out the index circuit so we can basically size our pipe, set our pump speed, all that kind of stuff comes into it, balance our system. Really important. And again, I'll focus a lot more on the modules itself, going through that as well, because some of the questions in that I think are really good questions that obviously we'll go through. The next verification webinar, there was one yesterday and seen quite a few people on that. is Wednesday, the 6th of August. So again, if you wanted to see how the umbrella service, the upgrades platform works from Heat Geek, we can talk you through that, show you all the apps, all that kind of stuff. If you were interested, not trying to sell it to you anyway. But again, they're upcoming there, and it's just the same Luma link where you just click on them and you can sign yourself on, all completely free, obviously. But yeah, if no one's got any questions, I'll finish it there. It's probably the first time I've actually finished these on time, which is a bit strange. But yeah, really appreciate everyone's time, and I really appreciate the interaction from everyone as well. As I say, everything that you need for that module, we've gone through there, so hopefully help people through that. But also the main thing is getting your understanding behind it all as well. So yeah, thanks for everyone's time. I really appreciate it, and hopefully I'll see you on the next one.
Cheers.
Cheers all. Thank you.
Cheers.
Good.
Yeah.